Welcome
to the Fractional Calculus seminars. Today we have Professor Changpin, who has earned his doctoral degree in computational mathematics from Shanghai University in 1988. He worked in the same university and became a full professor in 2007. He has been Glenn V. Sang Scholar since 2020 and fellow of the Institute of Mathematics and its application UK since 2021. His main research interests include numerical methods for fractional PDE and dynamics of fractional differential equations. He has presided over eight national natural science foundations of China, and he has published over 3 monographs and more than 150 papers in science journals, IMA Journal of Applied Math, Journal of Computational Physics, Journal of Nonlinear Science, Journal of Scientific Computing, Physical Review E, and Physics T, etc. We are very happy to have you here, Professor. You may please begin your talk.
Thank you, Pavan, for your invitation and introduction. In this talk, I will talk about Cyprus law diffusion. We will present analysis and computation for such kind of diffusion model. This is joint work with Dr. An Fan and Dr. Zhiqiang Li. They are both working in a different university now. The outline of this talk is organized as follows. We first give a brief introduction, what is ultra-slow diffusion, and we use which kind of calculus to characterize this kind of diffusion. Then we introduce long-term integration for fractional ordinary differential equations. Then we discuss logarithmic asymptotics to offer solution to fractional partial differential equations with the Caputo-Hadamard derivative. We also introduce a numerical method for initial boundary value problems. Okay, what is the ultra-slow diffusion? Ultra-slow or super slow diffusion was first named in this paper. This is in EPL. In fact, such an anomalous diffusion was observed a long time ago in igneous rocks in that year and linear dissipation in solids in that year. It was also observed in the wave attenuation in solid earth in the year. And its generalized version was reported in a recent paper. Okay. All of above, the physical processes have logarithmic asymptotics and are subordinated to the Leibniz logarithmic creep law. As far as we know, Hadamard fractional calculus is suitable for characterizing this ultra-slow diffusion. Now we introduce Hadamard fractional calculus. This kind of calculus was born in that year by Hadamard, a giant mathematician in France. Such kind of fractional calculus has members Hadamard fractional integral, Hadamard fractional derivative, and Caputo-Hadamard derivative. It's different from the fractional calculus. It's different from the integer order calculus. For the integer order calculus, we first introduce derivative, then integral. But for fractional calculus, we introduce a fractional integral, then fractional derivative. Okay, so such kinds of derivative are induced by the Hadamard fractional integral. So till now, there are some existing work. This is the journal paper, and this is the book, the Hodge book, and my group work since 2012. Now we introduce the Hadamard fractional integral. Ft is given, f of t is given, and it's a fractional integral with order alpha. This is the positive. It's given like this. This integration, dt over d tau over tau, and this is the kernel. If alpha is less than 1, it is weakly singular. This is not convolution kernel. By some variable substitution, it can be changed into a convolution kernel. Okay. For this definition, we require Ft in L1. This is just a sufficient condition, but it's useful in applied science and engineering. Okay. According to this Hadamard fractional integral, we can define Hadamard fractional derivative where given function f of t with order alpha. Alpha is this interval from n-1 to n. The given as follows. This is just fractional integral, then differentiation. So integration first in the Hadamard case, then differentiation. Okay. So this is integral, and this is differentiation. In the sense of delta, delta is not derived function. It's defined like this: delta and delta n and delta 0. For this kind of derivative, we require Ft in this space. This is the space of absolutely continuous function in this closed interval. This is just a sufficient condition. Okay. We can introduce another kind of derivative, Caputo-Hadamard fractional derivative. F of t is given, and it's order, and it's order with respect to derivative alpha like this. It is just change the order of the differentiation and the integration. So differentiation in the sense of delta derivative first, then fractional integration like this. Here you can see. So this is the delta. So this is delta. Okay. Here is tau d over d tau, and this is the tau d over d tau. Okay. We also require Ft in this space, in this space. But these two kinds of derivatives are not equivalent. Okay. We can find the relationship between the Hadamard derivative operator and the Caputo-Hadamard derivative operator. Like this. Okay, this summation is just the time expansion of f of t at the starting time a, in the sense of logarithmic function. Okay. If the initial condition is homogeneous, all of them are homogeneous, then two kinds of definition are equivalent. Okay. But for Caputo-Hadamard derivative, if a include minus infinity and Riemann derivative and the Caputo derivative are equivalent. So when we use a derivative, we must point out which is the starting time, which is the starting point. Otherwise, we can make some mistakes if we don't know when we start. Okay. In the following, we introduce another space of two kinds of derivative operator. This is the Hadamard derivative operator. Okay. From this, we can see alpha minus 1 is negative. So this is negative. You can see this is the alpha. Okay, negative. But for Caputo-Hadamard derivative, Caputo-Hadamard derivative operator, it is all of its power are positive. You can 0, 1, 2, n minus 1. Okay, they are something like the polynomials in the sense of logarithmic functions. Okay, from the null space of these two kinds of derivative, we can seek the definite condition for the evolution equation. Okay. Now we pose a condition for the fractional differential equation with the Hadamard derivative of order alpha in the interval. Okay. This is the equation, and this is the initial value condition. This is the fractional integral. This is fractional non-local. This is non-local, and we can give like this or this. So this condition is given pointwisely. From here, you can see UA may be infinity. Okay. Even if UA is 0. So we must give a condition like this or this. Okay. But really, we can give the initial condition like this T0. We can the U of T0, okay, equal to U0. But T0 is not the starting time. Not starting time. It's far away. It's far from the starting point A. Okay. But for the Caputo-Hadamard case, we can give an initial value condition like this. U of T at the starting time. Okay. So from the viewpoint of this, Caputo-Hadamard derivative is used in the applied science, and engineering. So we in the following we consider the Caputo-Hadamard derivative. Okay. Now we should long-term integration for the fractional ordinary differential equations. We first integrate two typical formulae for approximating Caputo-Hadamard derivatives over order alpha, i.e. L12 formula and L21 sigma formula. Okay. So in the interval, we consider the problem in the interval from A to capital T. We divided the interval AT into n sub-intervals. Okay, we want to find the exact we want to find its value at the node tk. Its value can be approximated by this summation with coefficients given as follows. Okay. Here we can see this partition is the uniform. Okay, we will introduce the various kinds of approximation formula for the Caputo-Hadamard derivative. Okay. Now we introduce the theorem. If ft in this space, okay, this is the time fractional derivative order alpha and uniform partition over the interval from A to capital T with the step size. The truncation area, the difference between them, this is the exact solution. The exact value, this is the approximate formula. Okay, so in the first sub-interval, the every order is 2 minus alpha. But in the following sub-interval, almost 3 minus alpha. Okay, 3 minus alpha. So we find this is the integer load. We will introduce another kind of approximate formula. This is sigma. Sigma is the positive since the alpha is in the interval from 0 to 1. So this is the positive. So this is the T sigma plus Tk plus sigma is not a integer load. We want to determine its value. We use the formula summation to approximate, okay, with the coefficients defined as follows. Then we give the error estimate for this case. The FT in this space and the time fractional derivative alpha in the interval, and this sigma, this time step is this step size, the truncated area is the difference between them. Here we approximate the derivative value as this point. It is not integer node. Okay, we get this. So the truncation area like this, almost 3 mass alpha. But if k equals 0, this may be higher than this, higher than 3 mass alpha. Okay. So what about the difference between the L21 sigma formula and the L12 formula? For the L12 formula, in the first subinterval, the error order is 2 mass alpha. For the following subintervals, the error order is 3 mass alpha. But for the L21 sigma formula, it is has the following estimation. But this is not integer node. Okay. Now we consider the following Lorentz system with Caputo-Hadamard derivative. It is the famous Lorentz system is the famous. It was derived from the Navier-Stokes equation. Okay, with choosing 3 modes. Okay. So this Caputo-Hadamard derivative with order alpha in the interval, and this t delta, b delta, c delta are intrinsic parameters. We show interest in this parameter value case. Since the classical Lorentz system has a chaotic attractor. Okay, we want to know whether or not this system has a chaotic attractor. Okay, this is the initial value, and we integrate this system in the interval. How to determine the chaotic attractor for the system? In general, we compute the first or largest near-apologist polent. If the first near-apologist polent is positive, then this system has a chaotic attractor. Okay. So we compute the first near-apologist polent for the Bow system, alpha, this is the order, the derivative order 1. And we use a dichotomy method to determine alpha value, which indicates the appearance of chaotic attractor. From this table, you can see for the cases, the first near-apologist polents are positive, but for the rest cases, the negative. So for that case, the system has a chaotic attractor. We can see from the phase diagram. In this simulation, we use the L21 formula to approximate Caputo-Hadamard derivative. So such a system has a chaotic attractor indeed for the alpha for such a alpha value. Okay, this is small value such that the system has a chaotic attractor. In the above discussion, we introduced the fractional ordinary differential equation. In the following, we show you into the fractional partial differential equations. We first consider initial value problem. Okay, initial value problem. So this is the linear model. Okay, Caputo-Hadamard derivative fractional operation. Okay. Alpha is the interval, and this fractional operation with the index s, and this is the initial value, ua of x, and the fourth term f of x and t, they are known. Since this is the linear model, so such a case can divide into two subcases. We can consider it's a homogeneous equation, and the homogeneous initial condition. Okay, since its solution, since the substitution has obeys the principle of homogeneous additivity, so we consider two subcases. This is a kappa of ds. D is the domain dimension. S is the index of fractional operation. That defined like this. Okay, so this is the critical value. Now, for the homogeneous equation, and this is the P in the interval, UP in the interval, and P less than the kappa of ds is the critical value, and the Q and L, and P, this is the initial value in L code. We have this estimation for the u of x and t. Okay, from this estimation, we can see that its solution has a logarithmic asymptotics. Okay, this is power. This is the power, and this is a logarithmic function. When p equals to the kappa and QR, this is the UA, this is the initial value condition, initial value function. We have this one. We have this one. If UA of x in L1, we have this estimation. This is a this is a norm in the weak form. Okay, so such a norm is the weak. Okay, if p equals to infinity, we have this estimate. So from this area, we can see that the solution has a logarithmic asymptotics. Okay. Now we consider the homogeneous initial value condition. That means UA equals to 0. This is the P. That is P. Okay. And this is the critical value kappa, and call R like this, and F in L code for any t. Okay. If F of x and t has a following decay condition, this decay, we have the following estimates. If gamma is not 1, then we have this estimates. Okay. If gamma is 1, we have this one. Okay. We have this factor instead of a logarithmic function. So in that part, we consider the linear case for the initial value problem. So what about the nonlinear case? Here we only consider semi-linear case, semi-linear model. Okay, showing the condition of the block and the global existence of a solution. Okay. Now we consider this model. This is the Caputo-Hadamard derivative with order alpha in the interval. This is the fractional function with the index in the interval, and the p here p is not different. It's different from the above. Here p is the power of u in absolute. Okay, let it p minus 1. Let p and this is the initial condition ua of x in this space. This means ua x is continuous in this space in the whole domain. But ua x approaches 0 when the norm of x approaches infinity. Okay. For this model, this is the nonlinear term, but this is a semi-linear model. We can define the mild solution for the Bow problem. This is the domain dimension and the time fractional derivative order alpha and the index of fractional function, and this is the power t and the capital T. And if UA in this space, we see UA with the U is a mild solution if U satisfies the following integral equation. This equation, this is the convolution. This convolution is with respect to the space variable x. Okay, variable x. GA of t, GF of t are green functions. They can be represented by the force function. Okay, they are hypergeometric function. Okay, this is the GI of t. This is the GF of t. That given like this. Okay, this is the force function. We can define another kind of solution for a partial equation. For a partial equation, we can define the various solutions. In the above, we define the mild solution. Here, we define the weak solution. Okay, this is the domain dimension. This is the derivative. This is the derivative order in time, and this is the index of fractional function and the capital T, and UA in L2, and the P is the power of U. Okay, this is the power. Okay, we call U is a weak solution. If U in space satisfies the equation below, like this. Phi is a trial function in this space with a complete support. Okay, and phi of dot capital T equals 0. This is the weak solution. Why we need a weak solution? If we define weak solution, so they are given in the integral form, so we can use lots of inequalities. Okay, so we need so in most numerical simulations and methods we use a weak solution. Okay. Then what about the relationship between the mild solution and the weak solution? U in this space. If U in that space is the mild solution, then U is also weak solution. Okay, in the weak solution. So from this theorem, we can use some various inequalities from in the integration to determine the solution's behavior. For example, blob and or global solution. Okay. Now this is the domain dimension. This is the time derivative order alpha, and this is the index of fractional motion. Okay, it's capital T, and you are in this space. Okay, but you are is positive, not always zero. Okay, so the following concurrence hold. UP in this interval, then my solution blows up in a finite time. The P. UP is bigger than this, and the initial value is sufficiently small, then the solution exists globally. Loosely speaking, small initial value, then global solution exists. So, if the initial value is not small enough, then a solution may blow up in a finite time. Okay. In the above case, we consider the initial problem, including linear case and nonlinear case. Now we introduce the initial boundary value problem. Okay, this is the initial boundary value problem. In the above discussion, we know this boundary value condition. But here we consider the initial boundary value condition. This is the Caputo-Hadamard derivative, the standard Laplacian. Okay, this is the short term, and this is the initial condition. This and this are known. Okay, the homogeneous boundary condition. We can find it's a closed form solution since it is a linear model. Now we introduce some integral transforms for the Hadamard integral and Hadamard derivative. Okay, this is the modified Laplace transform of f of t with the starting time a, positive. Okay, this is a modified Laplace transform. Then we can get an inverse modified Laplace transform like this. Okay, we can give it another kind of Laplace transform, the amended Laplace transform. Okay, we did like this. We have one more factor in the power. Okay, and the inverse amended Laplace transform, it can be got like this. Okay. If we have amended Laplace transform, sorry, this amended. Yes. You will have the amended Laplace transform. We can give another kind of integral transform. The amended Manning transform, like this, the Manning transform, and the inverse amended Manning transform. Why Manning transform is necessary? For the Fourier transform and the Laplace transform, we only pay attention to the asymptotics at infinity. Okay, infinity. But for the Manning transform, we can see for material we need to pay attention to the asymptotics at the starting point and the infinity point. Okay, infinity point. This is the amended magnitude transform and the inverse magnitude transform. We have these two kinds of amended integral transform. We have the very beautiful formula for this. So this is the amended Laplace transform. This is the amended main transform. We can see here is Kc. So this is a function with a variable Kc, but for this is also Kc. Clearly speaking, the one method Kc. Okay. Using the above, well-defined integral transform, we can get is the initial boundary value problem is a closed form solution. Actually, the explicit expression of the solution we get following the theorem. Okay, this is the time fractional. This is the time fractional derivative order alpha and epsilon. This is the initial value in this space, and this solution in this space, and the delta derivative of f in this space. Okay, we have the following. Then the equation 3.7 has only a unique solution and satisfy the following inequalities. This means space regularity, and this is time regularity of the solution. Alpha is the interval, but alpha is bigger than 1 or equal to 1, then this term approaches infinity. Okay, so this is initial asymptotics for the solution. Okay, so we pay attention to this case. From the above theory. Okay, I must get up. Okay, the solution U possibly has a weak regularity at the starting time. That is delta of t, delta square U of t, may blow up. Okay, at starting time. Or beta U at t is continuous at the starting time. In order to guarantee the time precision, one of choices is to use a non-uniform meshes. Okay, example, the gradient mesh. Okay, so divided the interval from A to capital T into M subintervals such that this is the load. Okay, this is load Tn. Okay, so we approximate this value. Use this one. These are coefficient. This is the non-uniform L1 formula for this derivative. Okay. This is the truncation. This is the truncation term. So this is the alpha and USD. So if this inequality, then the truncation error has this estimation. Okay. The optimal estimator here is alpha plus 1. Okay. In equation 3.7, have this initial asymptotic behavior. Have this. Okay. Now we for the initial boundary problem, we use a non-uniform L1 formula to approximate the time fractional derivative. Now we use local discontinuous Calocan finite element method to approximate the spatial derivative. So LTG method. LTG method is the first proposed in the paper. Okay. We introduce ordinary variable p. Okay, so the original system can be written in the lower order system like this. We can get the fully discrete LGT scheme. This is This is for the time derivative, and the rest for the space derivative. Here hat turn are so-called numerical fluxes. Okay, such choice is not unique. Here maybe can be a UHN plus and the minus. Okay. Now we get the numerical stable theory. The non-uniform L1 LGT scheme is numerically stable. Each initial value function. This is the source term. So from this you can see that the numerical method is stable. Okay, we're going to go the error estimate. This is UN is the weak solution, and this is a numerical solution. Okay, we have this. This is the precision in space, and this in time. This estimate is optimal. Okay. Now we use a numerical example. The starting time, 1. Okay, this one. The homogeneous condition. Initial condition is homogeneous, and the boundary technique is homogeneous. Okay, if the source term is given like this, it's an exact solution with S like this. We can see that such a solution has a weak regularity at the starting time, 1. That is that U of xt at the square U of x and t will blow up at the starting time. Okay. So we need to use a non-uniform L1 formula to approximate the time function derivative. We need to use. If we use a uniform division partition, we can the converted order in time is bad. Okay, we can see from the table the L2 long and the temporal converted order. Okay. This is R equals to 1. It means that the division in time from A to capital T is uniform. But here is alpha. So alpha, but the order, the converted order, less than alpha, less than, for this case, less than 0.4, and for this case, 0.6, and for this 0.8. Okay. If we choose the alpha like this, we can get a 2 minus alpha order in time. Okay, from this it's almost 1.6. Okay, 1.4 and 1.2 almost. Okay. The bar is for the linear model with the initial boundary value condition. But for the nonlinear, for example, semi-linear model, how to calculate its solution. So we choose this model, like this is time, this is Caputo-Hadamard derivative in time, and this special derivative. Okay, and U up to P. Okay, here P is the power. Okay, P is the power, is not the index of space. Okay, and this is the first term, and this is the initial value, and this is the boundary value. The boundary value is homogeneous. This is the so we can find this solution from A to capital T. Okay. A is the positive, and the UA is the positive. Since here is the U to T, so we must impose that the initial value UX is not negative. Okay, otherwise this term is defined it also can be said the condition is not well posed or better posed. Okay, better posed parabola. Here, P is bigger than 1. That's P. Now, in this model, we has a time version derivative in the sense of Caputo-Hadamard. We use another kind of L1 formula. The Pavan formula in the sense of logarithmic, that partition is different from partition here, from here. Here we directly divided the interval from A to capital T into n sub-intervals like this, okay? This L1 formula, different from the above, okay, can be, this girl, the lady comes from Pakistan, okay? This is my first female student from, this is my first female international PhD student, okay? So the Caputo-Hadamard derivative at the node Tn can be approximated like this. Okay, these are coefficients, defined like this. Such a L1 formula is different from the above. Okay, we use a various approximation formula for the Caputo derivative. Okay, this is the early work. Since this model is semi-linear, it may have a finite time blow-up solution. Even if no such a solution, no blow-up solution, its solution can be very sharp. Okay, we will see it later on. So we need to use moving meshes. Okay, so we use this equation. S dot means dx over dt. X means space. Okay, space and time in this time. And m tilde denotes the mesh density function. And tilde tau is a parameter. It is not step size. It is a positive parameter to adjust the mesh movement. Okay, one can obtain the time-dependent partition of the spatial interval. This is a standard interval. Okay, this is the moving mesh. So I just explained. So at a different time layer, for example, different time layer, the nodes, the interior nodes at a different time layer are different, okay, different. But the total number of nodes are the same. For the endpoints, that are unchanged, but the interior nodes at a different time layer are different. This is the basic idea of moving mesh. Okay. So at the time layer n, we can define the finite element space like this. So this is the subinterval. PL denotes the space of a polynomial, not over degree at the most L. This is the standard interproduct in L2 space, and the interpolation operator pi Ln at the time layer n, at the nth time layer, like this is H0 1i to the finite element space defined like this. Okay. So we can give about the wake form of the about nonlinear system like this. Okay. We need approximate the about equation at a time near Tn like this. Okay. In this talk and in our corresponding paper, we use interpolation projection pi Ln like this. Okay. We can use we can get a fully discrete schemes like this in the first time layer like this, and in the rest time layers like this. Okay. Why we use the UH tilde 0 and UH tilde J? Since at a different layer and the inter lows are different. So as that changed, okay, I changed. So we for the first time layer, we use this projection and this projection. Okay. The fully discrete scheme in this paper by choosing the L2 projection like this. Okay. But in our paper we should like this. You can see you know the tilde UHJ, U tilde TH. Here we can see from here you can see, but with different choices. In our paper, in our talk, we use this one. But in this paper, they choose like this. Okay, but our choice is better. Now we consider following seminar problem. Okay, this is homogeneous initial condition and homogeneous boundary condition. Okay, this is starting time. If the fourth term is chosen like this, we have a solution like this. This parameter, epsilon. Epsilon can be very small. It's a very small positive constant. Okay, this where it comes from? It comes from the source term. It comes from source term. Okay. Now we need to determine the density function m tilde. Okay, m tilde is given like this, and tilde alpha. Alpha is not derivative order. It is here tilde. Alpha tilde is the parameter. Okay, we go back to see equation 4.14. This is 4.14. We need to find this. Okay, this density and mass density function. Okay. Here for convenience, the calculation the linear move mass finite element linear element. So L equals 1. L equals 1. This is time Fernandez derivative order. This partition in time, this partition in space, and P the power of U, and this is the parameter tilde tau Okay. Epsilon is a parameter in the short term, or the first term f of x and t. Since the calculation is very complicated, so here in time direction, we use a uniform partition. Okay, we can obtain the following computer graphics. This is a numerical solution at t equals to 2. Okay, equal to 2. We can find. So the solution has a cusp here. Okay, it's sharp. So this is the mass trajectory. No, this is the layer. This is a layer, time layer, and time layer. You can see time layer. The masses, the total masses are the same, but the nodes, interior nodes, are in different positions. You can see here. Okay, the time layer, and the nodes. Okay. This is the numerical solution. Numerical solution. This is the exact solution. Okay. We also show the error for the Moore mesh finite element method. Okay. Here we use the tilt, the parameter tilt tau equal to 0.1 and epsilon in a function f of x and t like this. Okay, the two we find that there are two errors and space convergence order. Okay, this is the linear element, and the p is the power of u. Okay, we find center here. So the space convergence order is 2. They are almost 2. Okay, almost 2. And the time convergence order with m in time. Okay, this is the okay, this is in time. Okay, and this is a linear element and the power of u. Okay, u is positive. Okay, we get 2. It is the convergence order should be 2 mass alpha, but for small alpha, it's almost 2. From the analysis, it may be 2 mass alpha, so 1.75. For this case is 1.5, 2 mass alpha, 1.5, almost the same. This is the theoretical order is 1.25, but it is almost 1.25. Okay. This method and the technique can be used to numerically find a finite time blob solution and a quint solution, but we omit the details here. We only show the sharp solution for the system. The system under investigation is semi-linear, but no blob solution. We can use this technique to numerically find finite time blob solution and a quint solution. That's all. Thank you very much.
Thank you very much for the talk. For questions, please raise your hands. I will call out your name in the order they appear on my screen. Okay, I do not see any raised hands. So
Can I make one comment?
Please, Arran,
Yes.
go for it.
Just a remark from the theoretical point of view. The Hadamard fractional calculus, these operators of Hadamard derivative, Caputo-Hadamard, and so on, these are a particular case of fractional calculus with respect to functions. So these are fractional derivatives with respect to the logarithm function. And so sometimes you can start with a Hadamard differential equation and make a substitution like u equals logarithm of t, and you recover a classical fractional differential equation.
Thank you for your comment. For the typical diffusion, for example, for the typical diffusion with the algebraic asymptotics, we can use a Riemann type derivative, for example, a Caputo derivative. But for the silver flow diffusion, such a diffusion with logarithmic asymptotics, so we use a Hadamard, Caputo-Hadamard. We use a Hadamard type of derivative. Of course, Caputo-Hadamard derivative can be changed into the Caputo derivative with variables where the variables change. But if we change, we go with that change. It is difficult to. We can bring lots of the coefficients with depending upon the time or the space time at t and the domain variable at the space variable x. But we definitely consider such models. It is easier. We can find more problem to deal with.
Yes, so different behaviors can be modeled using this logarithmic type operators, but just from the mathematical side, it's good to be aware that they are a particular case of a more general theory that has a connection with classical fractional calculus through substitutions. Just a remark.
Thank you. It's true. Thank you.
I have one curiosity. So for your case of LDG scheme, what is the basis function that you are using?
We can see we give the null space of Caputo derivative and the Caputo-Hadamard derivative. You can see from this.
No. I'm asking what is the basis function. So you have UH belongs to the span of capital UH in your go to LDG DG scheme, I think.
Okay. Numerical scheme?
Yes. Where
Which one?
There was a slide that you showed numerical fluxes and you showed the discrete case. There was one slide.
Maybe the page I see.
No, I think DG was after. Yes, this one. Maybe
one?
next slides.
Okay.
Yes, this one. So you have this UH one slide behind the previous slide.
Yeah. The solution, the numerical solution depends on the initial value, initial condition, and the function.
Okay. This I understand, but I want to understand what is the basis function that you're using. You have a trial space, you have a test space.
But the solution may be in this and in this. Okay. In the condition, this condition.
No, this is the error estimate, but you have to discretize it, right? So you have some UH equal to sum of some coefficient, sometimes some polynomial. So what is this basis function that you are using?
How to say, and maybe we can see the numerical example here. This is a numerical example.
Okay.
Okay, numeric example. Okay, but you know, in this since it consider domain in time is a closer interval from a capital T, so we can use a where it's a estimation. So they are
So
in the consequence.
so look here in your previous slide you have UH belongs to some no, not this slide where you have the slide with the numerical flux. Uh, not this slide. Anyway, no.
The numerical flux.
Yes, exactly. So you have in your first line you have UH and PH and belongs to VH. So what is VH over there? What is the span VH? What is the definition of VH?
So you in a space we use a local discontinuous method, Calotin method. So we define the domain within given into many sub intervals, and at the interface, I mean the solution has some Hamilton dumps. So at the interface, so we need to use this. If we choose like this, we can get how to say in how to say there are lots of summation. There are some of the summation can be cancelled. Okay, we need to choose like this. Or here is UHN plus and THN minus.
Okay. Maybe I'll read your paper for the particular details for the definitions and things. So can you just point out to which paper is this?
In general for scientific computing.
Okay, it's the one in scientific computing. Okay.
Little paper, yeah. Journal of Scientific Computing.
I'll see. I'll go through this paper, and if I have further questions, I'll probably email it to you.
Okay, if you cannot find it, you can email me. Okay, I send to you.
Sure. Thank you very much, Professor.
I have two general questions, if you can ask.
Please go for it.
Please.
Two general questions. Let me start with the first question. If my understanding, I'm following the talk. In the beginning, you mentioned that the Hadamard fractional derivative describes better super slow diffusion. Can you explain why?
How to say? Thank you for your question. There are some there are some anomalous diffusion, but for the typical anomalous diffusion, the physical process behaves algebraic asymptotics. But for some kinds of diffusion, very slow. If we use the Caputo or Riemann or Caputo derivative, we cannot we cannot get a better result. Okay.
I see.
You from the paper I show you.
Is that related to the kernel?
Yes, it's the kernel. Yeah.
I see.
The kernel is the logarithmic kernel in the sense of logarithmic function. It is not convolution kernel. From how to say from here, this is super slow diffusion. Okay. In the viewpoint of random walks, and you can see from igneous rocks. So and went a long, very long time. So very slow. It's super slow. Okay.
Yes. My second question is, if you can go please to the equation number 411 and 412.
They say the 411.
Or 11, it's homogeneous boundary condition.
Homogeneous.
Yeah, 411. Yes, this one. Yeah.
Homogeneous.
Yes.
Mm.
Okay. Just a general question. Is the solution that explicit relation with the solution, is that obtained by separation of variable or another method?
Yeah, you're right. Yeah. Yes.
Which method you?
I mean, such solution is clear at the starting time, but it's a delta derivative will blow up at a certain time.
No, I mean, is it with a software or from separation of variable from mathematical methods? How
We
did you
use
find the method used to find f?
Palette is RTG. This is the palette element method in space and the non-uniform error method in time for the time fractional derivative. Yes, so we can consider non-homogeneous condition. We can change it then into the homogeneous condition, but then so the solution can be changing.
Okay. I see. Okay.
Okay, thank you.
Thank you.
Are there any more questions or comments? You may please unmute your mic if there are more. I assume there are no further questions or comments. So let me thank Professor Changpin Li. It was very nice to have you and for sparking this interesting discussion on this afternoon. Thank you very much.
Thank you all. Thank you all for your attention. Thank you all for coming. Thank you.
Thank you.
It was a
Thank
pleasure.
you.